potentially leading to a dense atmosphere capable of stabilizing surface temperatures and protecting against stellar radiation. Such conditions could make the planet either a temperate world or a hostile greenhouse, depending on the exact composition of its atmospheric gases. The cousin of Earth, as some have nicknamed it, orbits its star in 385 Earth days, placing it squarely in the habitable zone where liquid water could exist on the surface. This similarity in orbital period has captured the attention of scientists, as it hints at parallels with Earth's own climate dynamics. However, the additional 10% stellar energy received by the planet raises questions about whether it might experience runaway warming or, alternatively, maintain a stable climate through natural regulatory mechanisms like reflective clouds or a strong greenhouse effect. This distant world's host star is a G-type main sequence star, just like our Sun, but its advanced age offers valuable insights into the later stages of stellar evolution. The additional luminosity of Kepler-452 means that this elder sibling of Earth might have undergone significant warming over its history, potentially driving profound atmospheric and geological changes. If the planet ever harbored life, it may have needed to adapt to increasingly harsher conditions or retreat to more stable niches, such as underground environments or deep oceans. The massive exoplanet's geological activity is another point of speculation. A planet with its estimated mass and size would likely retain substantial internal heat, driving robust tectonic and volcanic processes. Plate tectonics, if present, would contribute to climate regulation by recycling carbon dioxide and stabilizing atmospheric conditions over geological timescales. Additionally, active volcanism could enrich the atmosphere with gases like water vapor and carbon dioxide, fostering a dynamic environment that might support a diverse array of ecosystems. The atmospheric composition of this alien world, though currently unknown, plays a crucial role in determining its habitability. A thick atmosphere with a balanced greenhouse effect could create temperate conditions suitable for liquid water, while an excess of greenhouse gases might result in a superheated environment akin to Venus. Conversely, a thinner atmosphere could leave the surface vulnerable to harmful stellar radiation, limiting the potential for life to develop. Future telescopes equipped with advanced spectroscopic tools, like the James Webb Space Telescope, aim to analyze such atmospheres, searching for chemical signatures that might hint at habitability or even life. This second Earth also serves as a reminder of the challenges in detecting and studying distant worlds. At a distance of 1,400 light-years, direct exploration is currently impossible, but spectroscopy allows scientists to infer details about its atmosphere and surface conditions. By analyzing the light filtered through its atmosphere during transits, researchers can identify the presence of key gases like oxygen, methane, or water vapor, which are potential biosignatures. The coexistence of these gases in disequilibrium would be a strong indicator of biological processes. Scientists are particularly intrigued by the potential for water on this super-Earth. Liquid water is considered the foundation of life as we know it, and its presence would greatly enhance the likelihood of habitability. If vast oceans exist, they could regulate the planet's climate, while also serving as cradles for early life, much like Earth's ancient seas. Even if surface water is absent, subsurface oceans heated by geothermal energy could provide stable environments for microbial life, similar to the icy moons of our solar system, such as Europa and Enceladus. The elder sibling of our planet is also a key to understanding the future of planetary systems. As its host star continues to age and brighten, its habitable zone will move outward, potentially making other planets in the system more habitable. Such shifts in stellar energy output provide critical insights into the evolution of planetary climates and the long-term potential for life. Comparing the conditions on this world to younger Earth analogs could help scientists identify universal patterns in planetary evolution and the factors that determine whether a world remains habitable. The discovery of this far-off cousin highlights the importance of missions like Kepler, which revolutionized exoplanet detection by using the transit method. This technique, which involves measuring the dimming of a star's light as a planet passes in front of it, has revealed thousands of exoplanets, each contributing unique insights into the diversity of planetary systems. As next-generation telescopes and observatories come online, the ability to study planets like this in greater detail will improve, providing answers to fundamental questions about their composition, climate, and potential for life. This celestial neighbor also drives innovation in space exploration and technology. Concepts like light sails, fusion drives, and even speculative ideas like warp drives are being developed with the ultimate goal of interstellar exploration. While direct travel to this world remains a distant dream, the drive to explore such planets inspires advancements that could bring humanity closer to the stars. This exoplanet, often referred to as a super-Earth or Earth's twin, is not just a scientific marvel but also a philosophical beacon. It challenges humanity to reflect on the possibility of life beyond our planet and our place in the universe. Its discovery suggests that Earth-like planets might be common, and with them, the potential for countless forms of life scattered across the galaxy. At the same time, the vast distances between these worlds remind us of the isolation of planetary systems and the immense challenges of reaching them. The study of this Earth analog pushes the boundaries of human understanding and fosters a deeper appreciation for the fragility and uniqueness of our own world. It serves as a reminder of the incredible complexity of the cosmos and the unyielding curiosity that drives humanity to explore the unknown. As we look to the stars and uncover worlds like this, we are reminded of the endless possibilities that await us in the vast expanse of space. The potential significance of Kepler-452b, often called a super-Earth or an Earth cousin, extends far beyond its physical characteristics. It opens the door to profound scientific and existential questions. Its discovery by the Kepler Space Telescope was a landmark moment in the hunt for planets that might harbor life, and it has since fueled interest in the search for habitable worlds across the galaxy. This distant planet, orbiting a star that resembles our Sun but is older and brighter, offers scientists a model for studying what happens to planetary environments as stars evolve over billions of years. The advanced age of its host star makes it particularly fascinating. Kepler-452, a G-type star like our Sun, has already been shining for approximately 6 billion years. This means that any biosphere on the planet would have had an additional 1.5 billion years to evolve compared to life on Earth. This extended timeline raises fascinating possibilities. If life emerged there, it might have reached levels of complexity or technological sophistication far beyond anything seen on our planet. Alternatively, the planet might illustrate the fragility of biospheres, showing how environmental changes driven by stellar aging could lead to the decline or extinction of life. One of the most intriguing aspects of this exoplanet is its potential atmosphere. While direct observations remain out of reach, theoretical models suggest it may possess a thick and stable atmosphere due to its larger size and higher gravity. A dense atmosphere could insulate the surface, regulate temperature extremes, and protect against harmful radiation from space. However, Its exact composition would dictate whether it supports conditions similar to Earth or veers toward the extremes of Venus. For instance, an atmosphere dominated by carbon dioxide could create a runaway greenhouse effect, turning the planet into a searing wasteland. On the other hand, a balanced mix of nitrogen, oxygen, and water vapor could sustain a temperate climate suitable for liquid water and, potentially, life. The planet's surface conditions, though speculative, are equally captivating. If it is a rocky world, as many models suggest, it might feature diverse geological landscapes shaped by tectonic and volcanic activity. The stronger gravity and thicker crust could lead to towering mountain ranges, deep ocean basins, or expansive plateaus. Tectonic activity, in particular, would play a critical role in recycling essential nutrients and stabilizing the planet's climate over geological timescales. Volcanism could replenish the atmosphere with gases like water vapor and carbon dioxide, which are crucial for maintaining warmth and potentially fostering ecosystems. This second Earth is also a prime candidate for exploring the role of liquid water in habitability. Water is essential for life as we know it, serving as a solvent for biochemical reactions and a medium for transporting nutrients. If the planet has oceans, they could regulate the climate through the absorption and redistribution of heat. These hypothetical oceans might also act as incubators for life, similar to Earth's early seas. Even if surface water is absent due to extreme conditions, the planet could harbor subsurface oceans heated by geothermal activity, akin to the environments on moons like Europa or Enceladus in our solar system. Kepler-452b's position within the habitable zone of its star adds further weight to its potential habitability. This Goldilocks zone is the region around a star where temperatures allow liquid water to exist on a planet's surface. The planet's orbital period of 385 Earth days places it firmly within this zone, but its proximity to an older, brighter star raises questions about its current climate. Receiving about 10% more stellar energy than Earth, the planet may have experienced significant warming over time. If it has mechanisms like reflective clouds or a dynamic carbon cycle, it might still maintain stable, habitable conditions. However, if these systems failed, the planet could have transitioned into a hotter, less hospitable state. The discovery of this exoplanet also emphasizes the importance of searching for biosignatures, chemical markers that indicate the presence of life. Future space missions equipped with advanced spectrographs aim to analyze the atmospheres of such distant worlds, looking for signs of oxygen, methane, ozone, or other gases that are out of equilibrium. For instance, the simultaneous presence of oxygen and methane in an atmosphere would strongly suggest biological activity, as these gases react quickly and would not coexist without being replenished by life forms. While the distance to Kepler-452b makes detecting such biosignatures extremely challenging, its study lays the groundwork for refining the techniques and technologies needed to probe exoplanetary atmospheres. Beyond its scientific allure, the discovery of this distant Earth twin has profound philosophical implications. It forces us to consider the possibility that life might not be unique to our planet and that the galaxy could be teeming with worlds harboring diverse ecosystems. It challenges our understanding of life's universality and resilience, as well as our assumptions about how civilizations might develop and survive in different environments. If advanced life exists, or once existed, on this faraway world, what could it teach us about our own future? And if the planet is barren, what lessons might it hold about the fragile balance required for life to thrive? This far-flung neighbor also serves as a powerful motivator for advancing space exploration. While it is far beyond the reach of current propulsion technologies, its discovery has inspired researchers to think creatively about how to overcome the barriers of interstellar travel. Concepts like light sails, antimatter propulsion, and even speculative ideas like warp drives are being explored as potential means of reaching distant stars. Although these technologies remain theoretical, the desire to explore planets like Kepler-452b drives innovation and expands humanity's understanding of what is possible. The role of this exoplanet in humanity's quest to understand the universe cannot be overstated. It represents a milestone in our search for habitable worlds and serves as a reminder of the vastness and diversity of the cosmos. While we may never set foot on its surface, studying its characteristics helps us refine our understanding of planetary science and habitability. It also highlights the importance of missions like the Kepler Space Telescope, which have revolutionized our ability to detect and study exoplanets. This distant super-Earth, sometimes referred to as an Earth cousin or a potential future Earth, has captured the imagination of scientists and the public alike. It stands as a testament to humanity's unyielding curiosity and desire to explore the unknown. As we continue to discover more about planets like this, we edge closer to answering one of the most profound questions of all: are we alone in the universe? Kepler-452b, often called Earth's older cousin, represents a milestone in our journey to understand the cosmos and our place within it. Its discovery raises not just scientific questions but also existential ones, forcing us to ponder the potential for life elsewhere and the future of our own planet. As we continue to delve into the mysteries of this distant world, every detail, no matter how small, adds another piece to the puzzle of understanding planetary evolution, habitability, and life itself. The advanced age of this planet's star, approximately 6 billion years, is one of its most fascinating aspects. For a system like this, the prolonged period of stellar luminosity increases the odds that the planet has undergone significant climatic and geological changes. If we consider Earth's history, where life took billions of years to evolve into complex organisms, the possibility arises that this distant super-Earth had even more time for life to emerge and adapt. However, this extended timeline also opens the door to darker possibilities, such as the complete extinction of life if environmental conditions became too harsh as the star aged and brightened. The larger size and mass of this exoplanet would fundamentally alter its physical and environmental characteristics compared to Earth. With a radius 1.5 times that of our planet and a likely mass at least 5 times greater, surface gravity would be significantly higher. This stronger gravitational pull could retain a much denser atmosphere, insulating the surface and potentially providing stable conditions for liquid water. However, the thicker atmosphere might also lead to extreme pressures, influencing the chemical composition, even the behavior of water, possibly creating supercritical states where water behaves neither as a liquid nor gas. These conditions might foster unique ecosystems unlike anything we've ever imagined. Its position in the habitable zone, often referred to as the Goldilocks zone, is central to its allure. The planet's 385-day orbit places it at a distance where stellar radiation could sustain liquid water without boiling it away or freezing it solid. However, the additional 10% energy it receives from its older and brighter star means that its climate dynamics would likely differ from Earth's. If the planet has mechanisms to reflect excess energy, such as extensive cloud cover or ice caps, it could maintain a relatively moderate climate. If not, it might face runaway warming, similar to what transformed Venus into a scorched and uninhabitable world. Speculation about the atmosphere of this alien Earth drives much of the scientific intrigue. If it contains water vapor, oxygen, or methane, it could indicate processes akin to those that sustain life on Earth. For instance, oxygen might result from photosynthetic organisms, while methane could indicate microbial activity. Alternatively, the planet might be dominated by carbon dioxide, hinting at volcanic activity or a less hospitable environment. While current technology cannot directly observe these gases from 1,400 light-years away, future telescopes equipped with advanced spectrographs might detect these chemical fingerprints, offering invaluable insights into the planet's potential habitability. The potential for water on this world remains one of its most captivating features. Liquid water is the cornerstone of life as we know it, and its presence would dramatically increase the chances of habitability. If the planet has vast oceans, these could stabilize its climate, much like Earth's oceans, by distributing heat around the globe. These hypothetical oceans might also serve as cradles for life, fostering the complex chemical reactions needed for biological activity. Even if surface water is scarce, the possibility of subsurface oceans, kept warm by geothermal activity, cannot be ruled out. Such environments, shielded from surface radiation, could provide stable conditions for microbial life to thrive. The geological history of this super-Earth is another area of intense scientific speculation. With its larger size and mass, it likely retained more internal heat than Earth, fueling prolonged tectonic and volcanic activity. Active tectonics could recycle key elements like carbon and nitrogen, maintaining a balanced atmosphere and preventing climate extremes. Volcanism could also release gases that contribute to a greenhouse effect, creating a warm and stable climate over billions of years. If such processes occurred, the planet might exhibit diverse terrains, from towering mountain ranges to expansive volcanic plains, providing a variety of habitats for potential life. This distant cousin of Earth also serves as a model for studying the effects of aging stars on planetary systems. As Kepler-452 continues to brighten with age, its habitable zone will gradually move outward. This means that while this alien Earth might currently be within the habitable zone, it may not remain there indefinitely. Understanding these changes could provide valuable insights into the long-term habitability of planets around Sun-like stars and what might happen to Earth as our Sun ages. The search for biosignatures on this world is one of the most exciting challenges for future science. Biosignatures are chemical markers, such as oxygen, methane, or ozone, that might indicate the presence of life. Detecting these signals requires advanced technologies and careful analysis, as non-biological processes can sometimes mimic biological ones. For example, methane can be produced by both microbes and geological processes, so its detection alone is not definitive proof of life. However, the simultaneous presence of oxygen and methane, especially in disequilibrium, would strongly suggest biological activity. Such discoveries would not only revolutionize our understanding of life in the universe but also raise profound questions about its diversity and prevalence. The immense distance of this Earth twin, at 1,400 light-years, makes direct exploration impossible with current propulsion technology. Yet this challenge has inspired innovative thinking about how to overcome the barriers of interstellar travel. Concepts like laser-driven light sails, fusion propulsion, and antimatter engines are being developed with the hope of one day reaching distant stars. While these technologies remain theoretical, the very idea of exploring such worlds drives technological advancement and fosters international collaboration. This far-off world, sometimes called the elder sibling of Earth, holds a mirror to our own planet's future. It reminds us that Earth, too, exists within a delicate balance, and changes in our sun's luminosity or our planet's atmosphere could one day alter its habitability. By studying exoplanets like this, scientists gain a deeper understanding of the conditions that make a world livable and the processes that can sustain, or extinguish, life over geological timescales. Beyond its scientific implications, this distant super-Earth captures the imagination of humanity. It challenges us to think about what might exist on worlds beyond our own and whether we are alone in the universe. It sparks dreams of exploration, innovation, and discovery, reminding us of the unyielding curiosity that defines the human spirit. As we continue to uncover the secrets of this extraordinary planet, it will undoubtedly remain a symbol of the infinite possibilities that await us in the vast expanse of space. This extraordinary world, often referred to as a super-Earth or an Earth twin, continues to captivate scientists and dreamers alike. The implications of its discovery ripple across numerous scientific fields, from planetary science and astrobiology to the future of interstellar exploration. Kepler-452b serves as both a scientific beacon and a philosophical reminder of the vastness of the universe and the endless possibilities it holds. One of the most tantalizing aspects of this planet is its potential to provide insights into the longevity of habitable conditions on Earth-like worlds. With its host star being approximately 1.5 billion years older than the Sun, the planet's environment may have already undergone stages of evolution that Earth has yet to experience. This makes it a valuable analog for predicting how Earth might change as our Sun gradually brightens and ages. Over billions of years, the warming of its star likely caused significant shifts in the planet's climate, possibly transforming it from a temperate, water-rich world into a harsher environment. These insights could help scientists better understand the delicate balance that sustains life and how planetary habitability evolves over time. The potential atmospheric composition of this exoplanet is another source of intrigue. The planet's greater size and mass suggest it could retain a thicker, more stable atmosphere compared to Earth. This atmosphere might act as a protective shield, mitigating temperature extremes and providing a stable environment for chemical and biological processes. However, the balance of gases within this atmosphere is critical. A high concentration of greenhouse gases like carbon dioxide could lead to a runaway greenhouse effect, creating a hostile environment similar to Venus. Conversely, an atmosphere balanced with oxygen, nitrogen, and water vapor could sustain conditions favorable for life, potentially resembling those on Earth. Spectroscopic analysis of this distant world, using next-generation telescopes like the James Webb Space Telescope, may one day reveal these secrets. The possibility of liquid water on the planet further elevates its status as a potential haven for life. Water is not only essential for known biological processes but also plays a vital role in regulating climate. If this super-Earth has extensive oceans, they could serve as thermal reservoirs, distributing heat across the planet and moderating temperature fluctuations. These oceans might also act as cradles for life, where early biochemical reactions could give rise to simple organisms. Even if the planet lacks surface water due to the intense energy from its star, there remains the possibility of subsurface oceans. These could be heated by geothermal activity, providing stable conditions for microbial ecosystems, much like the environments found beneath the icy crusts of Europa and Enceladus. The geological processes on this faraway cousin of Earth are another area of fascination. A planet with its estimated size and mass would likely have a dynamic interior, driven by heat from radioactive decay and residual energy from its formation. This heat could fuel robust tectonic activity, creating diverse terrains and recycling critical elements like carbon and nitrogen. Active plate tectonics, if present, could stabilize the planet's climate over geological timescales by regulating atmospheric carbon dioxide levels. Volcanism, on the other hand, could enrich the atmosphere with essential gases, contributing to a greenhouse effect that supports liquid water. These processes, coupled with the planet's size, might create a wide variety of habitats, from mountain ranges and volcanic plains to deep ocean basins. The planet's location within the habitable zone, often called the Goldilocks zone, is key to its allure. This region around a star is where temperatures allow liquid water to exist, making it a prime target for the search for life. The similarity of its orbital period, 385 days, to Earth's adds to its appeal, suggesting it experiences similar seasonal and climatic cycles. However, the increased energy it receives from its brighter star raises questions about its current habitability. If the planet's surface is shielded by reflective clouds or ice, it might still maintain moderate conditions. On the other hand, if its atmosphere has failed to adapt to the increased energy, the planet could have transitioned into a state of extreme warming. The search for biosignatures on this Earth cousin remains one of the most ambitious goals of exoplanetary science. Biosignatures are chemical markers, such as oxygen, methane, or ozone, that indicate the presence of biological processes. Detecting these signatures is a monumental challenge, given the planet's distance of 1,400 light-years, but advancements in spectroscopy and telescope technology offer hope. The detection of oxygen and methane in disequilibrium, for example, would strongly suggest biological activity, as these gases react quickly and would not coexist without continuous replenishment by life forms. Even the presence of water vapor or other volatile compounds could provide crucial clues about the planet's potential to support life. This distant super-Earth also serves as a catalyst for innovation in space exploration. While it lies far beyond the reach of current propulsion technologies, its discovery has inspired bold concepts for interstellar travel. Ideas such as light sails propelled by lasers, fusion-powered spacecraft, and even speculative warp drive technologies are being explored as potential methods for reaching distant stars. While these technologies remain in their infancy, the desire to explore planets like this one drives innovation and pushes the boundaries of what is possible. The very idea of interstellar travel unites humanity in a shared vision of exploration and discovery. Philosophically, this world challenges us to reflect on our place in the universe. It forces us to confront the possibility that Earth is not unique and that countless other worlds, each with their own histories and potential biospheres, may exist across the galaxy. The notion that life might thrive, or might once have thrived, on such a distant world prompts profound questions about the prevalence and diversity of life in the cosmos. If advanced civilizations have ever arisen on this planet, what might they have achieved during the billions of years of its existence? And if it is barren, what does that teach us about the fragile conditions required for life to flourish? This remarkable discovery also emphasizes the importance of preserving the conditions that make Earth habitable. By studying distant planets like this one, scientists gain a better understanding of the factors that sustain life and the delicate balance required to maintain it. These lessons are not only valuable for understanding other worlds but also for safeguarding our own. In every way, this far-off world embodies the spirit of exploration and curiosity that drives humanity to reach beyond its limits. It reminds us that the universe is vast, mysterious, and full of potential. As we continue to study this extraordinary planet, it will remain a symbol of hope and inspiration, a testament to the boundless possibilities that await us in the stars. The allure of Kepler-452b, often nicknamed Earth's distant twin, extends beyond its scientific intrigue, serving as a symbol of the boundless potential for discovery in the cosmos. Its very existence challenges our understanding of planetary formation, habitability, and the nature of life itself. While it is located over 1,400 light-years away, the insights gained from studying this exoplanet reverberate across disciplines, pushing the frontiers of human knowledge and imagination. As one of the earliest discovered exoplanets firmly situated within its star's habitable zone, this super-Earth has become a focal point for scientists searching for worlds capable of sustaining life. Its star, a G-type main-sequence star similar to our Sun, is not only older but also more luminous. This stellar brightness likely had profound effects on the planet's climate over billions of years. Early in its history, the planet may have enjoyed conditions strikingly similar to those of early Earth, with temperate climates, abundant liquid water, and a stable atmosphere. However, as the star aged and brightened, these conditions could have changed dramatically. This raises crucial questions about how long planets in similar circumstances can remain habitable, offering a glimpse into Earth's potential future as our Sun evolves. The sheer mass of this distant world suggests an entirely different physical reality compared to Earth. With an estimated mass at least 5 times greater, its surface gravity would exert a significantly stronger pull. This enhanced gravity would likely have profound implications for its atmosphere, enabling it to retain gases that would escape from smaller planets like Mars. A denser atmosphere might provide robust protection against cosmic radiation and stellar winds, preserving conditions necessary for life. However, it could also lead to extreme pressures on the surface, potentially creating an environment radically different from what we experience on Earth. The planet's geological activity is another fascinating aspect of its potential habitability. Its large size likely ensures a molten interior, sustained by radioactive decay and the residual heat from its formation. This internal energy could drive plate tectonics, which play a critical role in recycling essential elements like carbon and maintaining a stable climate. Volcanic activity, if present, might contribute gases such as water vapor and carbon dioxide to the atmosphere, supporting a greenhouse effect that could stabilize surface temperatures. The combination of tectonic and volcanic processes might also create diverse habitats, from underwater thermal vents to mountainous regions, providing numerous opportunities for life to develop and evolve. One of the most captivating possibilities is the presence of water, whether on the surface or hidden beneath layers of rock and ice. Water is fundamental to life as we know it, and its presence would significantly enhance the planet's potential for habitability. If vast oceans exist, they could regulate the planet's climate, distributing heat evenly and preventing extreme temperature fluctuations. These oceans might also foster complex chemical reactions, providing the conditions necessary for the emergence of life. Even in the absence of surface water, the possibility of subsurface oceans heated by geothermal activity remains compelling. These hidden reservoirs could harbor microbial life in stable, energy-rich environments, much like those found beneath the icy crusts of Europa or Enceladus in our own solar system. The role of the planet's position within the Goldilocks zone cannot be overstated. This region, where temperatures allow liquid water to exist, is a key factor in determining habitability. The planet's orbital period of 385 days is remarkably similar to Earth's, suggesting comparable seasonal cycles and energy input from its star. However, the increased luminosity of its older host star means it receives approximately 10% more energy than Earth. This additional energy could result in a warmer climate, potentially driving a runaway greenhouse effect if the atmosphere contains excessive amounts of greenhouse gases like carbon dioxide. Alternatively, if the planet has mechanisms for regulating its climate, such as reflective cloud cover or polar ice caps, it might still maintain temperate conditions. The search for biosignatures on this alien world remains one of the most ambitious goals of exoplanet research. Biosignatures are specific chemical markers, such as oxygen, methane, or ozone, that indicate the presence of biological processes. For example, oxygen is highly reactive and would quickly disappear from an atmosphere unless replenished by life. Methane, too, is unstable in the presence of oxygen and would require continuous production by either biological or geological processes. The simultaneous detection of these gases, especially in disequilibrium, would be a strong indicator of life. While the immense distance to this planet makes such observations extraordinarily difficult, advancements in spectroscopic techniques offer hope for future discoveries. The potential habitability of this alien Earth has inspired the development of next-generation telescopes and observatories. Instruments like the James Webb Space Telescope, the European Space Agency's Plato mission, and the planned Extremely Large Telescope are poised to revolutionize our understanding of exoplanets. These technologies will enable scientists to analyze the atmospheres of distant worlds, searching for chemical signatures that might indicate habitability or even the presence of life. By studying the light that passes through a planet's atmosphere during transits, researchers can detect the fingerprints of water vapor, carbon dioxide, and other critical compounds, offering invaluable insights into the planet's composition and climate. The philosophical implications of this faraway world are as profound as its scientific significance. Its discovery forces us to confront fundamental questions about our place in the universe. Are we alone, or is life a common phenomenon in the galaxy? If civilizations have arisen on worlds like this one, what might they have achieved, and how might they view the cosmos? Conversely, if this planet is barren, what does that tell us about the rarity and fragility of life? These questions challenge our understanding of existence and inspire a sense of awe and curiosity that transcends scientific inquiry. This distant cousin of Earth also serves as a powerful motivator for innovation in space exploration. While the planet itself is far beyond the reach of current propulsion technologies, its discovery has sparked renewed interest in the possibility of interstellar travel. Concepts like laser-driven light sails, fusion-powered spacecraft, and antimatter propulsion are being explored as potential solutions to the challenge of reaching distant stars. Although these technologies remain speculative, the dream of exploring worlds like this one fuels scientific creativity and pushes the boundaries of what humanity can achieve. The legacy of this remarkable planet lies not just in the data it provides, but in the questions it inspires. Its discovery reminds us that the universe is vast, diverse, and full of possibilities. Each new detail we learn about this super-Earth brings us closer to understanding the conditions that sustain life and the factors that shape planetary systems. As humanity continues its journey into the cosmos, this distant world will remain a symbol of hope, curiosity, and the unrelenting drive to explore the unknown. Kepler-452b, a beacon of exploration and wonder, continues to serve as a symbol of the infinite possibilities in the cosmos. Its very existence highlights the vast diversity of planetary systems and the tantalizing potential for habitable worlds scattered throughout the galaxy. As we learn more about this exoplanet, it deepens our understanding of the delicate interplay between planetary evolution, stellar aging, and the conditions that make life possible. This super-Earth represents not just a scientific discovery but a gateway to new realms of inquiry. Its larger size and mass, coupled with its position within the habitable zone, place it among the most intriguing candidates for habitability. However, these same factors pose unique challenges. The planet's stronger gravity would create conditions markedly different from those on Earth, influencing everything from atmospheric dynamics to the potential evolution of life forms. Any hypothetical organisms on its surface would need to adapt to higher pressures and stronger gravitational forces, potentially resulting in compact, robust life forms better suited to such an environment. The increased luminosity of its host star, an aging G-type star, provides critical insights into the long-term habitability of planets orbiting Sun-like stars. As Kepler-452 brightened over billions of years, it likely had profound effects on the planet's climate and atmospheric chemistry. Early in its history, this distant cousin of Earth may have enjoyed stable, temperate conditions, with abundant liquid water and a thriving biosphere. However, as the star's energy output increased, the planet could have undergone significant warming, challenging any existing life to adapt to the changing environment. This gradual shift mirrors what Earth may experience in the distant future, offering a unique opportunity to study the effects of stellar aging on planetary habitability. The potential for water, both on the surface and beneath it, is one of the most exciting aspects of this alien world. Liquid water is essential for life as we know it, serving as a solvent for chemical reactions and a medium for biological processes. If this exoplanet has extensive oceans, they could act as heat sinks, moderating global temperatures and creating a stable environment for life. These hypothetical oceans might also foster diverse ecosystems, with nutrient-rich waters teeming with microbial life or even more complex organisms. Even in the absence of surface water, the possibility of subsurface oceans, warmed by geothermal activity, remains compelling. Such environments, shielded from stellar radiation, could provide stable habitats for life to persist over billions of years. The atmosphere of this second Earth is another key area of speculation. A thick, dense atmosphere might insulate the planet's surface, maintaining a stable climate and protecting it from harmful radiation. The composition of this atmosphere, whether dominated by greenhouse gases like carbon dioxide or balanced with nitrogen, oxygen, and water, would dictate the ability. The atmosphere could sustain temperate conditions, while an excess of greenhouse gases might create a superheated environment. Observations of this distant world, made possible by next-generation telescopes, could reveal its atmospheric makeup and clues about its potential for life. The geological processes that shape this faraway world also hold scientific interest. A planet of gas would likely have an active interior, fueled by the heat of radioactive decay and residual energy. This internal drive plate tectonics, volcanic activity, and the recycling of critical elements like carbon and nitrogen. processes are essential for maintaining climate over geological timescales and for creating diverse habitats where life could emerge and evolve. Active volcanoes release gases into the atmosphere, contributing to a greenhouse effect that supports liquid water and temperate conditions. For biosignatures and cousin events, one of the most exciting frontiers in biosignature chemical markers that indicates a biological process. For example, oxygen is highly reactive to disappear from unless replenished by life. The presence of ozone or other compounds in disequilibrium could similarly point to biological activity. Markers requires and precise observations, but their discovery would revolutionize our understanding of the universe. Kepler-452b 1,400 light-years poses significant challenges for direct exploration, but it also inspires innovative technology in distant worlds. Concepts like laser-driven light sails, which use of light to propel space speeds, are as for interstellar travel. Propulsion and other advanced concepts, though still theoretical, represent humanity's determination to overcome the barriers of distance and time to reach the stars. While direct exploration of the world may remain out of reach for generations, its discovery fuels our collective imagination and drives progress in space exploration. The philosophical implications of this exoplanet are as profound as its scientific significance. It challenges us to rethink our place in the universe and consider the possibility that life might not be unique to Earth. If life exists, or once existed, on this distant world, what might it look like? Have evolved under conditions so different. And if the planet is barren, what lessons can we learn about the fragility of habitability and the factors that sustain life? These questions resonate deeply, inspiring awe and curiosity as we strive to understand the cosmos. Kepler-452b, often referred to as Earth's twin or the elder sibling of our planet, represents the best of humanity's scientific and exploratory spirit. It serves as a reminder of the vastness of the universe and the endless possibilities it holds. As we continue to study this extraordinary world, it will remain a symbol of hope, a testament to the unyielding curiosity that drives us to explore, and a beacon guiding us toward the stars. Each new discovery about this planet brings us closer to understanding the broader narrative of life in the cosmos, making it not just a scientific marvel, but a source of inspiration for generations to come. The story of Kepler-452b, sometimes called Earth's elder cousin, continues to inspire as it holds tantamount about the path and the dynamics of planetary evolution in the galaxy. This distant super-Earth symbolizes humanity's relentless curiosity, at gain from its study brings understanding the fundamental processes that shape habitable worlds. Though 1,400 the echoes of its discovery resonate across multiple disciplines, pushing the boundaries of science and imagination alike. This exoplanet's advanced age, tied to its host star's 6 billion-year lifespan, presents an extraordinary opportunity to study the long-term evolution of planetary systems. While Earth is nestled in the Sun's habitable zone today, scientists know that our star will brighten as it ages, eventually making Earth uninhabitable. 452b makes later stage of habitability, providing a glimpse of the challenges a planet might face as its host star grows increasingly luminous. Observations allow refining their models of stellar aging, planetary responses, shedding light on the delicate wire to sustain life over billions of years. The super-Earth's size and mass continue to draw speculation about its geological and atmospheric. With 5 times that of Earth and a likely mass 5 times greater, the planets gradually impact its physical environment. Crust and stronger gravitational pull might influence the types of landforms that develop, leading to unique geology unlike anything seen on Earth. Mountains could be deeper, while ocean basins potentially hosting vast underwater ecosystems. These factors would add atmospheric circulation, possibly driving more extreme weather patterns or stabilizing global temperatures. Planet's composition. Its atmosphere, though unobservable with current technology, is one of the most critical factors in its habit. This super-Earth likely enables it to retain a thicker atmosphere over time, even as stellar radiation gradually increases. This atmosphere might act as both a protective thermal regulator, trapping heat to create stable surface temperatures. However, the of the atmosphere is key. A high concentration of greenhouse gases, like carbon dioxide, might drive a runaway greenhouse effect to uninhabitable. On the other, balance of nitrogen, oxygen, and water vapor could sustain temperate climates and innovative life. Water is central to the intrigue surrounding this distant world. The presence of liquid water is considered a cornerstone of habitability. Planet in the Goldilocks, the possibilities or lakes on its surface. If oceans exist, they could regulate the planet's climate, distributing heat from the equator to the poles and preventing extreme temperature fluctuations. These water bodies could also serve as a habitat for microbial life or more complex organisms, providing the necessary medium for biochemical processes. Even if surface water is absent, oceans heated by geothermal remain a possibility, offering a haven for life shielded from stellar radiation and temperature extreme. Kepler-452b's geological activity, driven by its larger mass and internal heat, might be another critical factor in its potential habitability. The planet's size suggests it could retain significant geothermal energy, fueling active plate tectonics and volcanism. Tectonic activity would help recycle essential elements like carbon and sulfur, stabilizing the planet's climate over geological timescales. Volcanism, meanwhile, could replenish the atmosphere with water vapor and greenhouse gases, maintaining warmth and supporting a dynamic environment. These processes, coupled with a stable atmosphere, could create diverse habitats capable of supporting life. The search for biosignatures, chemical markers of life, on this alien cousin of Earth represents one of the most exciting challenges in exoplanetary science. Advanced telescopes and spectroscopic instruments are being developed to detect gases like oxygen, methane, and ozone in the atmospheres of distant worlds. The presence of these, particularly in disequilibrium, would strongly suggest biological activity. For example, oxygen would in an atmosphere without life, as it reacts quickly with other compounds. Similarly, the coexistence of methane and oxygen would indicate active biological processes, as these gases would otherwise destroy each other. Observing such markers on Kepler-452b would be a groundbreaking, revolutionizing our understanding of life in the universe. The vast distance to this distant super-Earth poses a formidable challenge, but it has also inspired a surge in innovative thinking about interstellar exploration. Concepts like light sails, which use beams of light to propel spacecraft at incredible speeds, are being developed as potential methods for reaching distant stars. Fusion propulsion and antimatter engines are also under consideration, theoretical solutions to the immense distances involved. While these technologies remain in the realm of the future, they reflect humanity's determination to explore worlds beyond our own, driven by the desire to uncover the secrets of planets like Kepler-452b. Philosophically, this alien world forces us to confront the possibility that Earth is not unique. The idea that there could be countless planets with similar conditions across the galaxy expands our understanding of our place within it. If life exists, or once existed, on this distant cousin, what might its universal processes? If it is barren, what does that tell us about the delicate balance required for life to emerge? These questions resonate deeply, challenging our assumptions about the rarity of life and inspiring awe at the complexity of the universe. The faraway twin also underscores the importance of Earth's habitability and the need to protect it. By studying worlds like this one, scientists gain insights into the sustained life and the factors that could lead to its decline. These lessons are not only relevant to exoplanetary science but also critical for addressing the challenges of climate change and environmental stewardship here at home. Kepler-452b reminds us of the fragility and preciousness of our planet and the imperative to preserve it for future generations. As humanity continues its exploration of the cosmos, this Earth twin will remain a symbol of hope and curiosity. It represents the unyielding drive to push beyond our limits, to seek answers to the most profound questions, and to uncover the mysteries of the universe. Each new discovery about this extraordinary world brings us closer to understanding the broader narrative of life in the cosmos. In its distant orbit, Kepler-452b stands as a testament to the infinite possibilities that await us among the stars. Kepler-452b, often referred to as a window into Earth's future, continues to fascinate researchers and space enthusiasts alike. Its discovery not only expands our understanding of planetary systems but also serves as a profound reminder of the sheer scale and diversity of the cosmos. As we piece together the story of this distant world, every new insight adds to the broader narrative of planetary evolution, habitability, and the potential for life beyond Earth. One of the most compelling aspects of this distant cousin is its potential to mirror what Earth might one day become. As its host star 452 has aged over the course of 6 years, it has increased. This gradual brightening likely caused the habitable zone to move outward, impacting the planet's climate and possibly its ability to sustain life. If the planet once had conditions similar to Earth, may now be undertones that hint at how our own world will evolve as the sun ages and brightens in the coming billions of years. Such a connection makes Kepler-452b an invaluable natural laboratory for understanding the future of Earth-like planets. The planet's size and gravity add layers of complexity to its potential environment. With a mass likely 5 times that of Earth, the planet's surface gravity would be significantly stronger. This would affect not only the retention of atmospheric gases but also the way life, if it exists, might adapt to such conditions. Organisms on this super-Earth might evolve compact and robust structures to counteract the effects of gravity. Meanwhile, the stronger gravitational pull would likely enable the planet to maintain a thick atmosphere over billions of years, even as stellar radiation increased. This thick atmosphere could act as a protect harmful cosmic and ultraviolet radiation while regulating surface temperatures. The question of water remains central to the intrigue surrounding Kepler-452b. If surface oceans exist, they could serve as stabilizing forces for the planet's climate, absorbing heat during periods of increased solar radiation and redistributing atmospheric circulation. These oceans might also support thriving ecosystems, providing the chemical processes that could give rise. On Earth, vents on the ocean floor are known to host rich microbial communities. Environments could potentially exist on this distant world. Even if the surface lacks water, subsurface oceans heated by geology could life-supporting environment from the harsher conditions above. The geology of this elder Earth is another area of immense interest. A planet of its size and mass would lack active interior, driven by significant geothermal energy. Plate tectonics, if present, play a critical cycling and stabilizing the climate. Volcanic activity might release gases like carbon dioxide and water vapor into the atmosphere, contributing to a greenhouse effect that maintains temperate conditions. These geological processes could also create diverse environments, ranging from towering mountains to deep valleys and expansive volcanic plains, offering a variety of niches where life might take hold. The potential atmosphere of this super-Earth is one of its most tantalizing mysteries. A thicker atmosphere could create conditions conducive to life by providing warmth, shielding the surface from radiation, and supporting a dynamic climate system. However, the specific composition of the atmosphere would determine the planet's habitability. If dominated by carbon dioxide, the planet could experience a runaway greenhouse effect, heating the surface. Conversely, a balance of nitrogen, oxygen, and water vapor could sustain temperate climates similar to those on Earth. Fused with advanced spectroscopes, like the James Webb Space Telescope and its successors, aim to analyze the light-passing atmospheres, potentially revealing the chemical fingerprints of life. The search for biosignatures, chemical markers that indicate the presence of life, on this distance the next frontier in exoplanetary science. Biosignatures like oxygen, ozone, or methane, particularly when found in disequilibrium, would strongly suggest biological processes. For example, oxygen is a highly reactive gas that would quickly disappear from an atmosphere unless continuously replenished by life. Similarly, methane is unstable in the presence of oxygen and would require active production to persist. These atmosphere of Kepler-452b would be a groundbreaking discovery, providing the first direct evidence of life beyond Earth. The discovery of this distant world has also sparked significant interest in interstellar exploration. While Kepler-452b lies far beyond the reach of current spacecraft, its existence motivates the development of advanced propulsion technologies that could one day make interstellar travel a reality. Concepts such as laser-driven light sails, which could accelerate small probes to a significant fraction of the speed of light, are already being explored. Fusion propulsion and other speculative technologies offer additional possibilities, reflecting humanity's determination to reach beyond the confines of our solar system. Philosophically, this planet challenges us to rethink our place in the universe. Its discovery highlights the possibility that life might not be unique to Earth, but rather a common phenomenon in the galaxy. If life exists, or once existed, on Kepler-452b, like follow evolutionary paths on Earth, or would it take entirely different forms? And lifeless that tell us about the world habitable. These questions push us to reflect on the fragility and uniqueness sphere while igniting a sense of cosmos. 452b also underscores the importance of preserving the habitability of Earth. By studying distant worlds, we gain a deeper appreciation for the delicate balance that sustains life and the potential consequences of disrupting it. The lessons learned from studying planets like this can inform our understanding of climate change, planetary ecosystems, and the long-term stewardship of our home world. As we look toward the future, this elder sibling of Earth will remain a focal point of scientific inquiry and exploration. It symbolizes the unrelenting drive to understand our universe and the infinite possibilities that await us among the stars. Each new discovery about Kepler-452b deepens our understanding of what it means to be a habitable world and what it might take to find, or one day visit, another Earth. It stands as a testament to the tenacity and ingenuity, inspiring future generations to look to the skies and continue the quest for knowledge. Kepler-452b, often dubbed a second Earth, stands as a beacon of scientific curiosity and human ambition, continuously inviting deeper exploration of its mysteries. Its discovery not only marks a milestone in the search for habitable worlds but also highlights the profound potential for life and planetary diversity across the galaxy. As our understanding of this distant world grows, so too does our awareness of the complexities involved in finding, studying, and potentially reaching planets beyond our solar system. This distant super-Earth offers a unique perspective on the relationship between planets and their hosts. With its star being significantly older and more luminous than the Sun, Kepler-452b provides a glimpse into the long-term evolution zones. Over billions of years, the increasing brightness of its star likely transformed the planet's climate, potentially shifting it from a temperate, water-rich world to one that is hotter and more volatile. These changes mirror what scientists predict will happen to Earth as the Sun continues to age, offering valuable insights into the future of planetary habitability in our own solar system. The planet's size and mass are central to its scientific intrigue. As a super-Earth, it occupies a category of planets larger than Earth but smaller than ice giants like Neptune. Its greater mass suggests a stronger gravitational pull, which would have profound implications for its atmosphere, geology, and potential biosphere. A denser atmosphere, long-term stability, protecting the surface from harmful stellar radiation and maintaining conditions suitable for liquid water. However, the stronger would also lead to extreme surface influencing the types of environments and ecosystems that could exist. These factors challenge our understanding of how life might adapt to conditions fundamentally different from those on Earth. Water, as always, lies at the heart of habitability. If Kepler-452b possesses surface oceans, they could regulate its climate, creating stable conditions where life might flourish. These oceans could act as reservoirs, preventing extreme temperature fluctuations and fostering the chemical reactions necessary for life. Water is absent due to the planet's proximity to its bright star. Subsurface oceans heated by geothermal activity could provide a stable, life-supporting environment. Earth, similar conditions are found beneath ice-covered regions and in deep-sea hydrothermal vents, where thriving ecosystems a harsh surface. The geometries of this super-Earth also an avenue for study. size and mass would likely retain significant geothermal energy, driving active plate tectonics and volcanism. These processes are essential critical elements like carbon and nitrogen, which play a key role in maintaining atmospheric stability. Volcanic activity could also release gases like carbon dioxide and water vapor into the atmosphere, supporting a greenhouse effect that stabilizes surface temperatures. These geologics, coupled with potential surface and subsurface water, could create a wide variety of habitats, each with the potential to host life. The planet's position within the habitable zone of its star is another point of fascination. Often referred to as the Goldilocks zone, this region is where temperatures allow liquid to exist on a planet's Kepler-452b's 385-day orbit places it well within this zone, but its older star's increased luminosity presents challenges. The additional energy it receives could lead to warming, potentially triggering a runaway greenhouse effect if its atmosphere contains significant amounts of carbon dioxide. Alternatively, reflective cloud cover or ice caps might help regulate its containing despite the increased stellar radiation. Atmospheric composition remains a critical unknown for Kepler-452b. A thick, stable atmosphere could protect the surface from radiation, regulate temperatures, and support a dynamic climate system. Specific balance of gases would determine the planet's habitability. For instance, an atmosphere rich in oxygen and water vapor could indicate Earth-like conditions, while one dominated by carbon dioxide might suggest a superheated, Venus-like environment. Spectroscopic studies using telescopes are expected to shed light on the planet's atmosphere, potentially revealing the presence of biosignatures, chemical markers of life. The search for biosignatures on this Earth twin represents a frontier in exoplanet science. Detecting gases like oxygen, methane, or ozone in disequilibrium would strongly suggest biological processes. For example, the coexistence of oxygen and methane, which react quickly with one another, would require continuous replenishment by life or non-biological processes. Water vapor, carbon dioxide, and other volatile compounds might also provide clues about the planet's climate and potential habitability. While the immense distance to Kepler-452b makes such challenging development of next-generation telescopes promises to bring us closer to uncovering its secrets. Kepler-452b's discovery has ignited discussions about the future of interstellar exploration. Although it lies far beyond the reach of current propulsion technologies, exists the pursuit of advancing distant stars. Concepts like laser-driven light sails, which could propel small at a fraction of the speed of light, are being actively explored. Fusion-powered engines and speculative ideas like warp drives also remain areas of intense research. While these technologies are still in their infancy, the dream of visiting or studying worlds like Kepler-452b continue innovation and drive progress. Beyond the scientific and technological implications, this distant planet challenges us to reflect on profound philosophical questions. Its discovery forces us to consider whether life is a common phenomenon in the universe or a rare occurrence unique to Earth. If life exists, or once existed, on Kepler-452b, what form might it take? How might it have adapted to the planets? Conversely, if the planet is barren, what does that tell us about the fragility of habitability and the fact life to emerge? These questions deepen our understanding of the cosmos and our place within it. Kepler-452b also serves as a powerful reminder of the importance of preserving the habitability of Earth. By studying other planets, we gain insights into the delicate balance of factors that sustain life and the consequences of disrupting that balance. These lessons are especially relevant in the face of global challenges like climate change, emphasizing the need to protect our own planet for future generations. As humanity looks to the stars, Kepler-452b will continue to stand as a symbol of hope, curiosity, and the unyielding drive to explore the unknown. Each new discovery about this extraordinary world brings us closer to answering some of the most profound questions about life, the universe, and our place within it. In its quiet, distant orbit, this elder sibling of Earth reminds us of the infinite possibilities that lie beyond the horizon, waiting to be uncovered by those brave enough to seek them. Kepler-452b, often seen as a mirror of possibility, continues to inspire humanity's imagination and scientific ambition. It stands as a silent testament to the vastness of the cosmos and the mysteries waiting to be uncovered. Every new theory or observation tied to this super-Earth sharpens our understanding of planetary formation, the prerequisites for life, and the future of habitability in a changing universe. It also fuels our collective dream of reaching distant worlds and understanding what lies beyond the familiar confines of our solar system. The aging star around which this planet orbits serves as a reminder of the cosmic timescales at play. Kepler-452, a G-type star like our Sun, has provided a relatively stable environment for over 6 billion years, offering ample time for any forms on the planet to develop and evolve. If biological processes ever took root here, they would have had far longer to mature compared to Earth. This extended timeline raises intriguing possibilities. What could a biosphere look like after billions of years of uninterrupted evolution? Could intelligent life have emerged and perhaps even declined as the planet's climate changed with the star's increasing luminosity? Or might microbial life persist in specialized niches, adapting to harsher conditions as the planet warms? The size and gravity of Kepler-452b introduce profound implications for and potential inhabitants. With gravity roughly twice as strong as Earth's, the physical and biological processes on this planet would likely differ significantly. Taller mountain ranges, deeper ocean basins, and more extreme weather patterns might define its surface. The higher gravity could also influence the evolution of life, favoring compact, squat organisms capable of withstanding the greater gravitational pull. If intelligent life